All right, so we're going to start off by looking at 6.3 part 3. So this is going to finish up the graphing that we were doing in parts 1 and 2. The only thing that's going to be different in this part is we're going to look at doing multiple transformations. Okay? And the order is the same that it always is. All right, so when you are graphing multiple transformations, that is generally the order we want to follow. If you want to see that kind of side by side with the equation, we can do that. Let's do C sine bx plus a plus or minus d. Okay, so I put down the 4 letters, and then I'll just kind of map it to what's over here. So your phase shift, that would be letter A. Your period change, letter B. Your vertical stretch, which is an amplitude change, that's controlled by C. And your vertical shift up and down, that is controlled by D. Remember that A and B are backwards. The bigger that you make A, the more compressed your graph gets horizontally. Okay. No, I'm sorry, B. The bigger you make B, the more compressed it gets. The smaller you make B, the more stretched it gets. With A, if you add a number, it's going to shift it left. Subtracting will shift it right. Okay. C and D are not backwards. If you put a big number in for C, it will stretch it bigger. A small number will compress it smaller. And D, positive number shifts up, negative number shifts down. And the only thing I didn't mention about B and C is if B or C is a negative, what does that cause your graph to do? Yep. Causes it to flip. Okay, that would be a reflection. B would be a horizontal reflection. C would be a vertical reflection. All right, so any questions on the order of the transformations? All right, so let's try an example. So all the problems that we do in this section are going to have either 2 or 3 transformations. But we're going to do them one step at a time. This is usually very easy when we follow it right away. We've had a little bit of a break from doing the other transformations. It's been a couple academic weeks. So let's see if we can remember how to do it. All right. Which one of those numbers are we going to deal with first? The pi over 2 inside or the 2 out in front? Yeah?
Pi over 2.
Right. We're going to deal with the pi over 2 inside. So for now, I'm going to do this problem. Sine x plus pi over 2. Okay. That is a phase shift. When you do a phase shift, which column stays the same?
Y.
Y. And does anybody remember what are the y values for sine?
0, 1, 0, minus 1.
Yeah, very good. Sometimes it's a little hard to remember with the break in there, but that's just we remember it. Good. Okay. Now, off to the side, I'm going to put my original x's. Does anybody remember the original x's? Yeah?
0, half pi, pi, 3 pi over 2, 2 pi.
2 pi. And now, what are we going to do to all of them to get my final x's?
Subtract half pi.
Yeah, so we're going to subtract pi over 2. Remember, this is not the final answer. This is just the first transformation. And then we're going to use that to do the second. All right, so we got negative pi over 2. 0. What's pi minus pi over 2?
Pi over 2.
Pi over 2. 3 pi over 2, take away 1 pi over 2.
Pi.
2 pi over 2, or just pi. And 2 pi, take away pi over 2.
3 pi.
3 pi over 2. All right. So there's our first transformation. Okay. Now, I'm going to do this one. Sometimes I use the same table. Sometimes I write it out as 2 separate tables. I'm just doing it separate this time. Okay, so now the 2, that is an amplitude change. What values are not going to be affected by this 2? Yep.
Zeros.
How about what column is not going to be
Oh,
affected?
why?
But yeah, 0 wouldn't be affected either. I wasn't specific. So yes, so yeah, say it again, which column is unaffected?
Y. No, the X.
No, x's. Okay, x's will not be affected by a vertical stretch. So copy your x's from the previous table. So negative pi over 2, 0, pi over 2, pi, 3 pi over 2. And what are we going to do to all the old y values to get the new ones? Yep.
Multiply that by 2.
Yeah, do it times 2.
Oh, easy.
And that's going to be my final y values. 0, 2, 0, negative 2, 0. And that's it. So that's how you do a multi-step. It's really just like doing 2 problems. All right, and our sketch. Let's see. I'm going to scale my axes to go by 2s. And on my x-axis, I'm going to label it using the values in that column, because those are all equally spaced. So we might as well use those for our labels. Now, plot all our points. So we've got 0, 2, 0, and then negative 2, back to 0. So that graph has been shifted to the left, and it has been stretched by a factor of 2. We don't notice the stretch because I scaled the axes. But that's so I don't have to use a giant piece of graph paper. Questions on that one? So notice the transformations there. There was one on each axis. One of them was a horizontal, or affected the x's. The other one was a vertical and affected the y's. Technically, when the transformations are on separate axes, it doesn't matter which one you do first. Okay? It's like the difference between like moving right and up, or up and right. You still would end up at the same spot. But to be safe, I would just stick with that order all the time. All right, let's try this one. This one, order has to be important. I know it's important because I see 3 transformations. That means there has to be 2 affecting the same axis. Okay. Which axis has 2 transformations on it? The x or the y? Yep.
The Y.
The y. Multiplying a number by 3 and adding 1 is not the same as adding 1 and then multiplying by 3. There's a difference. So we're going to have to be careful when we do the y's. So let's start with the x's. Now let's see if we can do the whole problem in one table. Final table. I'm going to put my original x's off to the side. And does anybody remember what we do with that 2 to get my new x's? We can either think of it as division, or you can think of it as multiplication. But you have to change the number if you do multiplication. So what do I have to do with that 2? Yeah? So, can you say it again? Okay, so you could flip it. You would make it, if you flip 2, what would you get? And then what would you do with the 1/2? Multiply. Yep, so you can either divide by 2 or multiply by 1/2. So that's going to give me 0. What's half of pi over 2? Pi over 4. Half of pi is, well, half of pi. What's half of 3 pi over 2?
3 pi over 4.
Yep. graph of 2 pi. And remember, the bigger you make this number, the more squished the graph should get. And this graph did compress. What's the period length of this graph now? It was 2 pi.
That's 5.
Now it's 1 pi. Yep. Okay, now our original y values. 1, 0, -1, 0, 1. That's for cosine. Based on that list, should we do the vertical stretch and then shift? Or should we shift and then stretch? Yeah?
Stretch, then shift.
Stretch, then shift. So that means we're going to times them by 3 first. And then after we times them by 3, we're going to add the 1. All right. And we're going to put our final answers in this table. Dex, what do I get for the first one?
4.
4. And the second one?
1.
1. Nick, how about the third one?
-4 or -2.
-2. And the fourth one?
1.
1. And the last one is going to be 4. And there's your graph. Oh, there's your table. Any questions on how we got the table for that one? All right, now let's do our graph. Okay, so I need to go as high as 4 and as low as -2. So I would go by 2s on the y. I don't have a line up there, but let's pretend like we have one. And -2. X's, they don't look evenly spaced because the denominators are different. But if they all had a denominator of 4, 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So they are all nicely spaced. All right, so let's use those labels. Okay, and when you write them, you should reduce them. Even though it makes the pattern harder to see, that's okay. All right, and plot your points. So we got 0, 4. Pi over 4, we are at 1. Pi over 2. Oh, I messed one up. I see what I did. I'll fix that. Pi over 2, I'm at -2. 3 pi over 4, I'm at 1. And pi, I'm at 4. I know I messed one up right away because I was looking at it. It didn't look like that V shape. It doesn't look symmetrical. And that's because I didn't put the first one in the right spot. Should be right there. All right, and make your sketch. Okay, remember, it's the dots look like a V, but remember it's part of a curve. Okay. Just like that. All right. Any question on that one? So that's we did a 2 transformation. That's a 3 transformation. I guess, does anybody want to see another multi-step one? Would order be important on that one?
Not exactly.
Technically, no. How come?
Because one only affects the x, one only affects the y.
Yeah, the transformations are isolated. Right? One's a horizontal, one's a vertical. You don't have 2 on the same axis. So, right, so you're going to be shifting the negative pi over 2 is going to shift it which way?
Right.
Yep, to the right, and the +5
Up.
up. So my graph is going to move right and up. That's why I made a grid in quadrant 1. Okay. All right, let's try some calculator stuff. So it says find a complete graph of 4 sine 3x and find the domain, range, amplitude, and period. Okay. Let's start with domain. What's the domain of any sine or cosine function?
All real numbers.
All real numbers. Right? When you draw a sine or cosine, it's a wave. It's connected. You never lift your pencil. There's no asymptotes. There's no breaks. No matter what you do to a sine or a cosine graph, for the types of transformations I just showed you, domain always stays the same. All right. Let's do the amplitude. All right, so this is something we talked about a couple weeks ago. Does anybody remember what number there has to do with the amplitude?
Is that the 4?
The 4? And what do we have to do with this number to get the amplitude? Yeah,
Take the absolute value.
take the absolute value. All right. So yes, we have to take the absolute value of that number in front. It's not that that number doesn't affect it if it's negative. It does. It causes a flip. But when you're talking about absolute value, taking a graph and flipping it doesn't change the amplitude. Okay. So what's the amplitude of this graph? Yeah.
4.
4. Yep. Amplitude is 4. Okay, so amplitude is 4. Range. Range is how high and low it's going to go on the y-axis. Has this graph been shifted up or down at all?
No.
No. So then it's going to be 4 times as tall as it normally would be. And it hasn't been shifted up or down, which means the range is going to be kind of symmetrical. Negative this number, positive this number. Okay. So what's my range going to be? Yeah?
-4, +4.
Including or not including?
Including.
Including. Now, it might not always be symmetrical. If, for example, you shifted that, say, up 2 units. You shifted it up 2, then instead of -4 to 4, it'd be -2 to 6. Okay? So you just have to pay attention if you do a shift with it, but we didn't. So we got domain, range, amplitude, and period. Does anyone remember the formula to find the period? Yep.
Isn't 2 pi divided by the stretch in the x?
Yeah, so in this case, it's 2 pi divided by
3, so it'd be
3.
2 pi over 3.
Yep. So actually, we don't even need a sketch for that. They still want us to find one, so we will. But that's the period. The period's important because they may ask you to find a graph on the calculator and say, for example, show 2 cycles. Okay. So let's do that. Let's graph that. And let's set our window so we show exactly 2 cycles. Okay. First, let's start with the y's. What should I use for my y min and y max? Yeah?
Something above, something below -4 and something above the 4.
Yeah, if I go like -5 to 5, that'll be good. And now I want to show 2 cycles. Let's start with how long is 1 cycle of this graph? Yep,
2 pi over 3.
2 pi over 3. So how big would 2 cycles be?
Multiply that by 2 would be 4 pi over 3.
Yeah. So the easiest way to show 2 cycles would be to make a sketch and have it start at 0 and end at 4 pi over 3. And if you do that, you should see exactly 2 cycles. There's 1, 1.5, 3/4, and 2. Okay. Did it say to show 2 cycles? No. Just if I'm not given directions and they say graph it on the calculator, that's generally what I do. I just show 2 cycles. Any questions on the window I used to get that. Now, there is one thing I should have made sure of, but I didn't need to check this because my calculator was already all set. But what's something you should always check when you do your graph? Yep.
Radians or degrees.
Right. If this is in degrees, you're going to see an awful picture, okay, on the window we just used. That doesn't look like a wave at all. It looks like it's just a straight line. If you want to do it in degrees, that's fine. But you need to adjust your period to be in degrees. In degrees, 2 pi over 3, that's 120. So if you want to see 2 cycles, you need to go all the way to 240. Okay, that's a lot bigger than what we had before. But now, it'll look exactly the same as the other graph, just by adjusting my period. I would say generally, most graphs are going to be in radians, not degrees. Okay. All right, let's try another one. Okay, find a complete graph, and then domain, range, period, amplitude. Okay, all the same stuff. Okay, start with domain. What's the domain of 3 sine x minus 1? Ryan.
All real numbers.
All real numbers, yeah. Okay, let's do the range. All right, what's the range? Sometimes it's easier to find the amplitude first, but this one, I think we can get the range first. Yep.
-3, 3.
-3 to 3. Okay, as long as you haven't done a shift up or down, those numbers, it's going to be symmetrical. Okay. Domain range, amplitude is 3. Good. And period, 2 pi. There is no period change in this problem. Number in front of x is a 1, so there is no stretching or compressing horizontally. Okay, let's do a sketch. 3 sine x minus 1. If you don't adjust your window, it's not going to look right if you're trying to show 2 cycles.
So it's 4 pi.
Yeah, so let's do 0 to 4 pi. Now, we're going to break a cycle in kind of a weird spot because we've shifted it to the right 1 unit. That's fine. We're just not going to see the wave starting on the x-axis. So let's see what we get. So we get 0 to 4 pi. Y min and max are still okay. So see what I mean? It's not starting where it normally was. But it's going to end right there, and we're still going to see 2 cycles. If you wanted to make it start at a nice spot, like let's say you wanted to have it start here and show it ending over here, you'd have to adjust your window to be 1 unit to the right as well. And you could do that by doing
Just subtracting one, I imagine.
a +1
Or subtracting.
and a +1. If I adjust the window by 1 unit to the right, now the window lines up with where the graph moved, and it looks more like what you're used to seeing for 2 cycles. Okay. Any questions on that? So there are a couple identities that we're going to start to talk about. We're going to use them more throughout the year. But this first identity basically allows us to change a sine into a cosine. Okay. Let's graph just basic cosine. And I'm going to do zoom 7. That is if you want to think of that in terms of sine, it's a horizontal shift of sine. take this. So that's cosine. Let me trace it. Where does the graph of sine normally start? If you don't shift it, stretch it, just basic sine, yeah?
0.
Yeah, normally starts at the origin and then goes up from there. So let's think about the blue one. If you wanted to turn the blue one into the red one, which way would you have to move it? Well, which way could you move it the shortest amount and turn the blue one into the red one? To the left or to the right? Yep.
To the left, or the blue one or the red one? The blue
We
one
want
would
to turn
be-
the blue one into the
okay,
red
yeah.
one.
The blue one would be shifted right.
Yeah, we could shift it to the right. And if you shift something to the right, would that be a plus or a minus? A minus. And then, how much of a shift is it? Yeah?
Pi over 2.
Yeah, it's exactly 1 tick mark or pi over 2 off. So we can turn the blue one into the red one. Now let's think of it the other way. Let's turn the red one into the blue one. If you wanted to turn the red one into the blue one, which way would the red graph have to slide? Michael?
Negative pi over 2.
Yeah, if you did a negative, that would move it pi over 2, and we could turn the red one into the blue one. So whether you want to do a plus pi over 2 or a minus pi over 2, you can do it both ways. But you can turn sine into cosine, and you can turn cosine into sine. So let's take the graph of sine, and let's shift it to the left by pi over 2. And when you do that, you get exactly cosine. That's why it traces right on top of it. So numerically, that's thinking of it graphically. That means if I wanted to find, let's say, the cosine of 50. Now let's do this in degrees. I get that. That's the cosine of 50. Since I'm going to do this in degrees, what's pi over 2 the same as in degrees? Wait.
I was not raising my hand, but I'll take a guess. Is it 30 degrees?
No, that's pi over
It's
6.
45 degrees, right?
That's pi over 4.
Uh, 60 degrees.
That's pi over 3. Yes, that's 90. So based on that, instead of taking the cosine of 50, I could take the sine of what? And it would come out exactly the same. Think about the cosine of 50 would equal the sine of what plus 90. That's one way to think about it. Think about what x would have to be, and then simplify what's inside there. Yep.
If x is 50 degrees, then cosine of 50 is equal to sine of 140. Once
So
add
what number would you put in that box?
50.
So 50 plus
50 degrees plus 90 degrees.
like that?
40 degrees.
All right, let's try it and see what happens. Sine of 140. There we go. We got the same answer. Yeah. All right. So that's, again, that's not really a proof of it. It's just showing you that if you have a cosine, you can get the same answer doing a sine. All right? And same thing here. If you had the sine of 30, what would that be the same as? Instead of doing the sine of 30, I could do the cosine of what? Yeah?
Cosine of 30 degrees minus 90.
30 degrees minus 90, which is?
Negative 60.
Yeah, negative 60. And if you don't like dealing with negative angles, then what can you add to that to make it positive?
Add 360, so you get 300.
Yeah, so we could do cosine of 300. So there's all different ways we can manipulate a problem in trig to get the same answer, but write it with a different function. Okay? And that's what these identities are important for, helping us to take something and manipulate it and change it to something else. Because maybe we're doing a problem where for some reason we can't work with cosine. We have to work with sine. Well, we can change cosine to sine using this identity. All right. And now let's finish up by solving a few equations on the calculator. All right. When you are solving a trig equation, there's one of two ways to think about it. You're either going to write just certain answers, or you're going to try to write every answer. If I put sine x in y1 and I put 0.4 in y2, sine x, it's just going to be a wave that continues like that forever. What's the highest that that wave ever goes? Yep.
1.
1. There's no transformations to it. What about 0.4? If I put that in y2, what's that going to look like? Put 0.4 in y2. Yeah,
A straight, like, horizontal line.
it's going to be a horizontal line. And it's definitely below 1. That's the highest the wave goes, so it might be somewhere around there. If I wanted to write down every solution to this problem, how many times will the line and the wave cross? Yep,
Infinitely many.
infinitely many. So when we want to write down all solutions, all we have to do is find the first two. And we know that that solution, let's make that the blue one, the blue solution is going to repeat again right there. How much later does an answer repeat? In general, not a specific number, but in general, the answer will repeat every what?
Period.
Every period. Yep.
2 pi in this case.
In this case, it would be every 2 pi. So the blue one is the answer where the wave is heading upward. So that's a blue one. That's a blue one. There's another answer, and that's where the wave is heading downward. That answer is also going to repeat every cycle. So if you want to find all solutions, all you have to do is find the solutions in the first cycle, and then tell me that those two answers repeat. In this problem, they're not asking you to find all solutions. They are basically telling you, set your window from 0 to 2 pi, and write down every answer you see. In this case, just in the green box. So that's what we're going to do. All right. We're just going to write down the answers we can see in a certain area, and we're going to forget that there's infinitely many. But it's important to remember that there are. Okay. All right, so let's graph that. So we're going to put in sine x. We're going to put in 0.4. And remember, you want to set your window to what they're telling you. Why did they write the window like that? Greater than or equal to 0, and then a less than 2 pi. Yep.
Because if there's an answer on 2 pi, which in this scenario there is, they don't want us to include that answer.
Right, you don't want to repeat the blue answer. That's not a different answer than the first one, right? That's the answer to the blue one in the next cycle. So if you're going to include the left edge of your window, then don't include the right edge. Okay, when you're trying to set up a window that's one cycle. When you type it in, you're still just going to put 0 to 2 pi. But you want to keep in mind not to include that second answer, even though you're going to see it. Window, -4 to 4. We could get away with -2 to 2. Okay, so I didn't get a very good picture. How come?
In degrees.
Still in
Degrees.
degrees.
I'm in degrees. Okay, we are not doing this problem in degrees. I can tell that because of the window. It is in radians. If it was degrees, it would have had a little circle. Okay. So how many answers do we get per cycle?
2.
2, right? 2 answers. So we're going to do second calc intersect. Do the first one. Put that over there. And do second calc intersect again. This time, move your cursor more than halfway. That should be good enough. And there's the second one. Okay, so the 2 answers are 2.73 and 0.41. What was the original problem? Sine of x equals 0.4? I could have done that a lot faster without graphing. We haven't learned this yet. But if I do this, you'd still be putting in your window, and I already have the answer. Okay. So there are faster ways to do this than graphing. But then the thing is, how do you get the second answer? We'll talk about that at some point. But it has something to do with this, adding pi to it. No, I'm sorry, not adding pi.
Half a period?
Subtracting pi from it. 2.73, 2.73. But why did I subtract 0.411, the first answer, from pi to get the second answer? We'll talk more about that at some point.
Is it because it's the first cycle, so you're removing that space from that first cycle? Like it's the first answer in the cycle? Or is it the same way?
It has to do with the fact that this answer is in quadrant 3. If you were to look at the angle, 2.73 radians, it's an angle that's in quadrant 3. And it's positive. So the fact that it's positive and in quadrant 3 tells me something important, which I'll teach you at some point, but not today. All right, let's look at this one. I'm just going to write this window a little bit. Let's go from 0, oops, less than or equal to x, less than 2 pi. Okay, same window as the last problem. Okay, let's put in our y1 and y2. And we want to remember that if these two lines cross, how many times do they cross each other? If you could zoom out forever. They cross infinitely many times. So either one of two things happens. They either cross infinitely many times, or they do not cross at all. How could they not cross at all?
It was higher than the
Yeah,
wave.
like that.
Or lower.
Yeah, so if the wave is higher or lower than the line, well, then they don't cross. So we've got 2 cosine 0.5x. Now, normally, would the cosine function hit a horizontal line at 1.5? What do you think? Would the cosine function normally hit a horizontal line at 1.5?
No.
No? How come?
Because, oh wait, no, never mind. It will.
I like your first answer better. Let's stick with that.
I think.
Why wouldn't a cosine function normally hit a horizontal line at
Oh.
1.5? Just
I
a
was
regular
looking at
cosine.
the top one.
Yep.
Regular cosine function wouldn't hit the line, it wouldn't hit y of 1.5 because it only goes up to 1.
It goes to 1. But this one is going to hit because we've done a vertical stretch of cosine by a factor of 2. So because of that, it will hit somewhere, probably only one time though, because that 0.5 is causing the graph to stretch. So it's not cycling fast enough to get another intersection point with the red one, at least not in that window. Okay, so this one only has one answer. And it's 1.445. All right, let's try this one. So this one is 2 trig functions. The other 2 that I gave you so far, those would be pretty straightforward to solve by hand. This would be a little harder. What makes this hard algebraically is you have 2 different functions, sine and cosine, and the arguments are not the same. When you want to start working with trig functions, it really helps if the arguments are the same. So we'll talk about how we could maybe do a problem like that, but it's not something we're going to look at algebraically right now. All right, so I'm going to do 3 cosine 0.5x, 2 sine x. Window's usually 0 to 2 pi that they give you in these problems. Might have to set my window. Well, might be okay. Yeah, just barely. I think I need to set my y min and max a little higher. But I think you could tell how many solutions are there going to be? 3. Yep. Is there any question how you would find all 3 solutions? When you do the intersect, does it matter where you put your cursor? What do you think? Joe, does it make a difference where you put your cursor when you do the intersect here? No? Okay. Well, yeah, it does it wherever it's closest to. So if I want to get all 3 of them, then does it make a difference where I put them? Yeah, I need to put my cursor closer to each one as I do them. Yeah, but you will get 3 answers. All right. And the last one, what's different here? Moises, what's different in this one? It's an inequality. When we write our answer to an inequality, we write it as an interval. So now we got to think about brackets and parentheses, stuff like that. Okay, possibly a union if there's 2 sections that we need to look at. So 2 cosine x and negative 1.3. Okay, we are looking for where the wave is above the horizontal line. Oops. How many sections is the wave above the horizontal line? Yeah, 2. Okay, we need to look at 2 sections. This one, call section 1, and this one, section 2. Let's just start setting up the interval. Okay. We're going to have 2 sections, so that means we're going to need what symbol in the final answer? Yep.
The u.
Yep, we need the u. Now let's start with interval 1. Can we include or not include the left endpoint of interval 1? Maddie, what do you think? How come? Right. Anyone else think we can? If can support that, or if you don't think we can, tell me why we can't. Yep.
You can include it because the like area of the graph you're looking at includes the 0.
Yes, it does include that. So we definitely can include that. How about the end of interval 1? Can we include that or not include it? No, why not?
Because you're only looking at where it's greater than, not greater than, or equal to.
You're only looking at where it's greater than the red line, not equal. So that's how interval 1 is going to look. Now let's do interval 2. Include or not include the start point for interval 2. What do you think? Maddie, what do you think?
We can't include it.
How come?
Because it won't be above it, it'll be on it.
Right, we cannot be on it. We have to be above the red line. So not include. How about the endpoint for interval 2? Include or not include?
Include.
What?
Include.
How come?
Because it is above the red line.
So for the endpoint for interval 2, it is above the red line, but there's something else we need to.
Oh, it's not. It's less than 2 pi.
It's at the edge of the window, and you can't include the edge of the window. So we already know interval 2 ends at 2 pi, and we know where interval 1 starts because it's the other edge of the window. So interval 1 starts at 0. Now we just have to find where interval 1 ends and interval 2 starts. So that's our intersections. So interval 2 starts at, we'll just call it 4. And interval 1 is going to end on 2.28. Okay, and why did I have to write my answer as an interval rather than just like x equals and a number? Yeah.
Because you're not looking for a specific point, you're looking for a segment.
Yeah, I'm looking for this entire section because it's an inequality. Yep. All right, so that finishes up 6.3. Okay, so tomorrow, 6.4 will be the last section we do this week that looks at graphing, and that's all the other trig functions. And we only spend 1 day, so we don't go into as much depth with the other ones. So that is the homework for tonight on 346. Take a look at that first thing tomorrow. First test for term 3 will be on Friday, and I plan to be after school this week on Thursday.